The following presentation is going to be primarily aimed at students who are currently in basic electricity courses. We're using the book by Floyd, and we're going to review parallel circuits. The chapter outline is resistors in parallel, total parallel resistance, voltage in a parallel circuit, applications of Ohm's law, Kirchhoff's law, current dividers, power in a parallel circuits, and troubleshooting. And the objective is to identify parallel resistive circuits, determine total parallel resistance, determine the voltage across each parallel branch, apply Ohm's law in a parallel circuit, apply Kirchhoff's current law, use a parallel circuit as a current divider, determine power in a parallel circuit, and troubleshoot parallel circuits. It's important that you understand when you see key terms in your textbook that those are in fact key terms and they're important. So you need to know the meaning of parallel. You need to know the meaning of branch. You need to know the meaning of Kirchhoff's current law. You need to know what a node is. And you need to know what a current divider is. Now, let's start off very simply. Let's start on page here, paragraph 5-1, resistors in parallel. When two or more resistors are individually connected between the same points, what does that mean? Here's the same point. This resistor is connected here, and this resistor is connected here. Up here, these two resistors are connected to the same point, aren't they? So when two resistors are connected in parallel, then you have or form a parallel circuit. The two currents come back together at point A. Let's start those from Vs. They flow here. They flow from here, and they divide. And then they flow here, and they divide. So you have parallel currents. They're starting at the node B. They're flowing from node B up through resistor resistor R1, and over through resistor R2. Here they combine back together. Now notice that the current that's coming out of the battery is going to be equal to the current going into the battery. So IT and IT coming out of the battery is going to be the same current that's going back in the battery, IT. Now let's look again and let's watch a current flow through three resistors. As you might note, current flow is the important subject here, isn't it? Because current flow determines what will be the total voltage across your resistor. Is that right? No, that's not right, is it? What is right? Vs will determine the total voltage across each resistor. In a parallel circuit, what is constant? The voltage is constant. So if I have 25 volts as Vs, I'm going to have 25 volts at point A and B. Across R2 it will be the same. Across R3 will be the same. And across R4 will be 25 volts. All will be the same voltage. In a parallel circuit, the voltage is going to be constant. Now, let's go a little further. Let's start to talk about the drawings and the schematic diagrams of parallel circuits. Notice here, I'm going to move this up a little bit so you can see it. Unfortunately, this camera is not very wide. This is an old camera, and it only sees a certain portion. It uses the television standard. Well, notice here that this particular circuit on 5-2, for those who have textbooks, on 5-2 is drawn a little different than we had previously. The ones we had previously were drawn more like this. But that still makes this a parallel circuit. For notice the current. The current will come out of the top, which will be A. Now remember, before we had the battery going the other way. The current will flow from negative through this branch, the first branch, to the positive. The current will flow from the negative through this branch and back to the positive. Now remember, the current coming out of the circuit, or out of the battery rather, is going to be the same as the current going back into the battery. Now this is a more standard form that you and I have discussed before, but here we have the negative side of the battery. We have it at the top. Now it doesn't have to be that way. We could have just as well put the negative at the bottom and the plus at the top. The reason they did that, quite frankly, is to fool you a little bit. They want you to be able to see that there's not all circuits going to be the same. They're not going to be drawn the same, but they're actually electrically the same. Now, let's look at this circuit. Is this a parallel circuit? Well, of course it is. And once again, we have the power supply here. And that's the negative side. Remember, the short plate is the negative side. And the long plate is the positive. So this is plus, this is minus. So current is going to flow out of A. It's going to flow into this node, and it's going to flow two places. It's going to flow this way, and it's going to flow this way. The two together will flow back into the battery, the plus side, and what will happen? The currents will once again, the current flowing out of the battery is going to be the same as the current flowing into the battery. Now let's take another look at the drawing. Now remember, all of these have been parallel circuits, and they will continue to be parallel circuits. So let's move this over a little bit. Unfortunately, there's not much room there. Now look at this. Is this a parallel circuit? It sort of looks like a series circuit, doesn't it? But it's not. Remember, here's our battery. This is the plus side, and this is the negative side. Current's going to flow out of A. It's going to flow to the node. Then it's going to flow to this branch, this way. And it's also going to flow to this branch, isn't it? So that's just another way of drawing the same thing that we had in the previous example. When you see that, you need to analyze the circuit, and the way you do that, you analyze it by how current flows, not by how it's drawn. Too many people are fooled when they actually see the schematic. They're not sure if it's a parallel or a series circuit, but the way they can tell, of course, is through the current flows. Now let's go ahead and turn the page. Right now you should be on page 174 of your textbook. And let's see if I can focus this. If I can't, then I'll just read it. Well, I can't. Unfortunately, it's too narrow. So what I will do, I'll move it down to a circuit, and I'll read that to you. But of course, don't just let me read to you. What you should be doing right now, you should have your textbook before you, and you should be following what I'm doing. Now, it starts off by saying, when resistors are connected in parallel, the total resistance of the circuit decreases. And the total resistance of a parallel circuit is always, very seldom do you hear the word always, but is always less than the value of the smallest resistor. So what that means, if we have two resistors, let's say here, let's see if you can see that. Yeah, you can. Okay, let's say here that R1 is 5 ohms and R2 is 10 ohms. How much will the resistance in that circuit be? Well, you can't come up with a numerical figure yet, can you? You had 5 ohms and 10 ohms. But using the reciprocal formula, you will always end up with less than the smallest. In this case, this was 5 ohms and this was 10 ohms. So in your mind, you should say, I have less than 5 ohms. If you have more than 5 ohms, then you know that you've made a wrong calculation. Now, the formulas that I want to discuss are real important. This is probably the most important formula we're using in this chapter, and you're going to be using it probably throughout your career. This is the reciprocal formula. And basically what that means is that the total resistance in a parallel circuit, now I'm talking only about a parallel circuit, I'm not talking about a series circuit, and I'm not talking about a series parallel circuit. I'm only speaking of a parallel circuit. And you notice here the reciprocal formula. And what that is 1, just the number 1, the numeral 1, divided by the reciprocal of R1 plus R2 plus R3 on out to however number of resistors that you have. Now, that's basically what I want you to know right now at this time. That's all I really need you to know. Now, what we're going to do, we're going to go down and we're going to calculate the resistance in this circuit. Now, notice that I have, in this circuit, I have a 100 ohm resistor, I have a 47 ohm resistor, and I have a 22 ohm resistor. Approximately, how much resistance will that total circuit be? Approximately, how much will RT be? Well, we know that it's going to be less than what? It's going to be less than the smallest resistor, and the smallest resistor here is 22 ohms. So we can start our calculations. And we're going to end up, after we use the reciprocal formula, we're going to end up with the idea that the total resistance there is 13 ohms. Now, you must be able to work problems like that. Okay, you notice here that we've gone through conductance. I'm not really interested in this moment other than the idea of conductance. Conductance is the reciprocal of what? Of resistance. That's how we came up with our formula, where 1 over RT equals 1 over R1 plus plus plus. Now, if you understand that, that's all at this time that I need you to understand about conductance. Now let's go ahead and talk about your calculator. Some of you, I notice, have had a problem with your calculator, and I can't get this down to where I want it, so I'm going to push this over to where I've written something. Now, on our calculator, TI-30XA, we have a reciprocal function there, and it's called 1 over x. Well, I want you to note on some calculators that the reciprocal key is x to the minus 1, or first power. Now let's turn the page here and let's go on. Again, I want you following along with me. I'm not going to do all the work. You're going to have to do some of it. Now, we discussed earlier that the reciprocal formula is the one that I would like to see you use. Why? Because it covers every case. Now, there are different cases of where a resistance can be covered with a different formula. For example, and this is only for 2 resistors, if you have 2 resistors in parallel, and we can determine the total resistance by this formula, that RT equals R1 times R2 over R1 plus R2, and that's called the what? The product. The product, R1 R times 2 over the sum. It's called the product over the sum formula. And the total resistance of 2 resistors in parallel is equal to the product of 2 resistors divided by the sum of the 2 resistors. Now, again, you can use that if you want to. I would advise that you don't. I would advise for now, at this stage in your career, that you use only one formula, because you don't need any more than that. You can work every parallel problem using the reciprocal formula. Now we're going to talk about a couple of more formulas, and you can of course use those too. And the one we're going to talk about now is this formula here, where RT is equal to R divided by N. Now let me clarify that a little bit. When you have more than one resistor, you can take the resistance, and this is, let me clarify, use this formula only in the case where the resistance are the same. For example, if you had 100 ohm resistors, all 100 ohm resistors here, you can use this formula that we discussed. We can use the formula that RT equals R over the number of resistors. Okay, in this case, R is equal to 100 divided by how many resistors? 1, 2, 3, 4, 5. By 5. And the total resistance there is going to equal 20 ohms. Now we could have done exactly the same thing with the reciprocal formula. I know I've noticed that some of you, for some reason, like to do the formula that we mentioned previously, the product over the sum, when you only have two resistors. And you can. That's not a problem. And when you have problems like where you have 5 or 6 resistors and they're all the same value, some of you still want to use this formula that RT equals R, the resistance of one of the resistors, over the number of resistors. And it works. It does work. There's no question about that. But what I'm suggesting to you, as time goes on, you will be inundated with more formulas than we're talking about now. And eventually, it would be good if you could use one general formula. Now, at one time, when people had to do the mathematics longhand, and God forbid that happens again, what you had to do, you had to divide numbers into 1. Now, once you get proficient at it, that's not a difficult thing to do. But until you do, there's plenty of room for error. So what I would suggest to you is, even when you have resistors that are easy to work in your problems, that you don't use that. That what you do, you use what? The reciprocal formula and your calculator. Because you will always get the correct answer using the reciprocal formula. Now, let's go on a little bit. Let me move this up if I can get it all the way up. I don't know if I can. Unfortunately, what I'm doing here, I picked up an old Elmo machine. I think most of you who have been in school recently consider this an ancient machine. And it's called an Elmo reader. And most of you have seen these. And it has a camera at the top. And it does a fair job. But unfortunately, it's got a television type format. And as a consequence, I can't do a widescreen with this. I have a widescreen camera. I'm thinking about going back to that. But this Elmo for me is so convenient, and I'll talk to you later about that. That's a different story. But now let's look at resistors in parallel. One way to represent resistors in parallel is with this area here by saying R1, and these two lines mean that the resistors are in parallel. So R1 is in parallel with R2, which is in parallel with R3, which is in parallel with R4, which is in parallel with R5. Indicates that R1 and R2 are in parallel. Well, we know that, don't we? This notation is also used with resistance values. For example, if you have a 10K resistor, we use that symbol in parallel with and in parallel with a 5K ohm resistor. Now, you don't see the benefit of that yet, but I'll show you when we go into series parallel problems that's quite convenient. Now, one advantage of a parallel parallel circuit over a series circuit is that when one branch opens, the other branches are not affected. Let me give you an example. The old Christmas tree lights, I don't know, some of you are too young to remember the old Christmas tree lights, but some of you, of course, are familiar with trying to find out what bulb is bad in a series circuit of series Christmas lights. What happens in a series circuit when one bulb goes bad, the entire circuit will open up. Well, I think I've lost my camera. Hold on a minute. What's happened there? I think something has gone wrong. Are you still there? Okay, I see it's back. Now, what we're going to do, I'm going to try to put this into perspective here if we can. What this is a diagram of an automobile. And it shows that these circuits are in parallel. Notice these lights? Okay, these are the headlights. Okay, this is the battery here. These are the headlights. This is a fuse, remember? And this headlight is in parallel with the other headlight. And here's the off-on switch. When you turn your headlights on, current will flow from negative to positive up through the headlights and through the light switch, which will be closed to the plus side. Now, if in fact you were in series and the parking lights went out, what would happen then is that if the parking lights went out, if you were in series, then your headlights would go out also. And of course, that wouldn't be a good thing. Let's go on. Let's now look at a circuit in your house. This is not part of your DC theory. This is AC theory, but it works on the same principle in what we're talking about. Now, notice here that we have 120 volts. Up here we have a circuit breaker. That's a symbol for a circuit breaker. You'll get that in AC theory. Now, here we have one light bulb. This light bulb is hooked up in parallel. Okay, let me tell you what color codes are. It's not important now, but in your house you primarily have a black and a white and a bare wire, which is copper. Now, in this case, this light bulb is hooked from the white to the black, which puts it in parallel with the input of 120 volts. Now, notice over here we have another light bulb hooked up exactly the same. Here you have some outlets hooked up the same. These circuits are all in parallel, because if they were in series and one went out, every light in your house would be out, every appliance would be off. So that's why we want to. That's another reason for using a parallel circuit. Now we're going to skip some of this. I'm just going over the points that I consider salient to what we're doing right now. And what I want you to do, I want you to go to 5.3, and I want you to make sure you understand this. This is an important point. The voltage across any given branch of a parallel circuit is equal to the voltage across each of the other branches in parallel. As you know, each current path is in parallel. Now, there's a point that you need to remember. You'll see that again, I'm sure. All right, let's move on. Now, it's easy to tell parallel circuits. Let's look at this. Remember, we discussed parallel circuits before, and what we said that the voltage will be the same across each component. Note here, this is a battery. We call it V source, VS, and here the voltage across across G and B will be the voltage across A and H. If you have a 10-volt battery, then the voltage from B to G will be 10 volts. The voltage from C to F will be 10 volts. The voltage from D to E will be 10 volts. Sounds boring, doesn't it? But it's not. It's one of the important facts that you need to know in order to understand parallel problems. Okay, let's go to an example. I could do a lot of drawing here, but unfortunately my drawing is not that great. And as a consequence, I'm going to just use the text. Okay, let's look at this. Okay, here we have a parallel circuit. Notice that it's set up a little differently than you've seen previously. Notice that the battery is not at the end like we've demonstrated before. But nevertheless, we could put that battery at the end. It doesn't matter where that battery's at. Okay, and I want you to see here, though, this is an important fact. Consider no voltage drop across this fuse. So the voltage across the battery at this point and this point will be 25 volts. The voltage across this resistor R2 from this point and this point will be 25 volts. Let's call this nodes. So the voltage across this node and this node are the same. The voltage across this node and this node are the same. The voltage across this node and this node are the same. Same for this node and this node. So we know that the voltage is going to be 25 volts all along this line. 25 volts from negative, which is ground, to positive. Okay, so let's look at how current's going to flow. We could have just as well moved this resistor down to this other end. We could have drawn that in as this, but we're not going to. It's good where it's at. I just want you to know that it doesn't matter where you have any of these resistors. The current flow is going to be the same. Now, let me erase this out of my textbook. So maybe I can get more at the bookstore for it when I turn it in. I don't turn it in. Actually, I keep my books. And you probably should do the same. This is a great book. It'll serve you for many classes. Okay, let's look again. What we want to do is to figure out, determine the voltage across each resistor. We've done that, haven't we? Because we've said that V1 equals V2. Let me move this up a little bit so you can see that. We've said that V1 equals V2 equals V3 equals V4 equals V5 equals V source, which equals 25 volts. Now I hope all that made sense. I'm going to have to answer this phone. Thank you for calling. I'm going to have to delay talking to you, though. I'm in the middle of a video. Goodbye. I apologize for that. I could have stopped the recording, but last time I did, I lost the entire thing. Okay, now let's go on. We're going to talk about the application of Ohm's law in these particular circuits, in these parallel circuits. And Ohm's law can be applied to parallel circuits, and you're going to see that Ohm's law in a parallel circuit, you're going to be able to find the total current in parallel circuits. You're going to be able to find the branch currents, and you're going to be able to find the voltages and resistance in parallel. Now, how do we do that? As I discussed with you earlier, and I can't overemphasize this, use your calculator. We want to, now here in the book, they have used RT equals R1 times R2, R1 plus R2, called the product over the sum. But if I were you, even though they've worked it here like that, I would go ahead and I would use my calculator. I would use a reciprocal formula. Now notice here that current is going to flow the same way. Again, I've discussed this before with you. This ground is actually, you can think of it as a wire, one solid wire. All it is, ground in this case, is going to a piece of metal. Let's say in your automobile, in your headlights. Coming out of your headlights, you'll have a lead that goes to the battery, the plus side of the battery, and on the other side you'll have a lead that goes down to the chassis, which means the metal part of the car. On your automobile, the negative side of the battery is hooked to your metal part of your car. So any current that flows out of here is going to flow up through ground into this branch. And this is still going to be a node here, and this is going to be a node here. Now let's figure out RT. In this case, they have used the product over the sum, and you can see the figures. I'm not going to go into that. I'd assume you use your reciprocal formula using your calculator. But let's look at this. Current's going to flow out of the negative side of the battery. It's going to flow through the chassis or the ground, and it's going to flow. This is going to be a node here. This is going to be a node. It flows up through the node, through the 100 ohm resistor, and forms a branch. You and I have discussed before, the example I used was a river where it has a creek coming off of it, and some parts of the country it's called a branch. So if you relate to that, that's a good reminder of how to remember what a branch is. So the current flows through the node, up through the resistor, and that's called a branch. Also, current will flow another direction. Current is going to flow through the ground once again, up through the resistor, dropping positive to negative, and this is negative to positive. And those two currents are going to join back together. And here's I want to reemphasize again, the current flowing out of the battery or the power source will be called IT. And the current flowing back into the battery is going to be IT. So the current flowing out of your power source is going to be equal to the current flowing into your power source. That was a fairly easy problem, wasn't it? And in this case, we said that RT, we figured that out, and then we used the battery voltage of 10 volts, and we used Ohm's law that IT equals Vs over RT. In this case, it was 10 volts, Vs, and some of you are using E, which is okay. That would be E over R. I equals E over R. It's the same thing. So 10 volts divided by 35.9 ohms equals 279 milliamps. Now remember, a milliamp is 1/1000th of an amp. So that's a small current. Okay, now let's see what happened. That current is the total current going through these two branches, correct? That's IT. Now, we can go on, and we could do another example, but I want you to do that on example 5-9 and work that out. I want you to look at the results of it, and I want you to see that I1 is equal to Vs over R1. That's the current in the first branch. And now we're looking at example 5-9. Let me see if I can get that to work in there. I don't think I can. Maybe. No, not quite. Anyway, look in your textbook at example 5-9, and you'll see that the currents are through I1 is going to follow Ohm's law. We're going to use Ohm's law to solve the currents, and they're quite evident. I'm not going to go through each of these. I'm sure that you've discovered that I equals E over R of one of the resistors. And again, we use V source, because why are we using the same thing, V source, all the time? Why are we using 20 volts all the time? Because in this parallel circuit, the voltage is equal to the source, isn't it? It's the voltage across each component in a parallel circuit is equal to the source voltage. Now, very simply, what I would do if I were you, it's very easy to go ahead and write your formulas first. That's what I would do. And I would then use my calculator to calculate the currents. Now, once you've calculated the currents, you're going to discover that by adding these currents together, that you're going to have the total current. It's going to be the same as IT. So IT in this case is equal to I1 plus I2 plus I3. Now let's go ahead and look at another problem. This time we're going to use the reciprocal formula. We're looking at this circuit. It is indeed a parallel circuit. Now notice that the current in this case is given. This current is 37 milliamps. This is the current flowing back into the battery. Okay, so that tells me that I also have 37 milliamps coming out of the battery, going through each. We're going to add those up. They're going to. We'll see in a minute. We'll see how that adds up. Let's go ahead and work the problem first. So we do the RT, and we came up that RT equals 136 ohms. Now that we see that RT equals 136 ohms, we can calculate the voltage of the source, because we know, what do we know? We know IT because that's given right here, isn't it? Now let's see if you can see that. Because IT is given, so we know the current, the total current, and we don't know the voltage yet, but we're going to calculate the voltage, aren't we? So we know the total resistance, and we know the total current, so we can use the formula that V source, or V total, equals I total times R total. And we had 37 milliamps times the total resistance was 136 ohms. So the voltage across Vs is 5.05. I hope that you're following this. If you're not, be sure to send me an email or see me after class. This is the crux of what we're doing in this class for about the last 2 weeks now. Let's look on. The problems are fairly simple and straightforward once you get certain methods down together. Now, what we're going to do, we're going to move on to a useful tool that's in our tool bag for solving these circuits. And what we're going to look at is Kirchhoff's law. Okay, Kirchhoff's law says that a voltage law, it's a voltage law that deals with voltages in a single closed loop. Now that's what we have in a parallel circuit, isn't it? A single closed loop. And Kirchhoff's current law applies to currents in multiple paths. And that's what we have in the entire parallel circuit. Now let's think about that. Let's review a little bit. Remember series circuits? That's what Kirchhoff is talking about in the voltage law, because he's saying that the voltage drops across each component algebraically will add to be zero. And here in the current law, Kirchhoff's current law, he's going to show us how to work with multiple currents. Now let's look at the actual law itself. Now Kirchhoff's current law says this, and it's abbreviated KCL. The sum of the currents in a node, remember the node is the point where the current goes into a parallel circuit and divides. The total, that's the total current in, is equal to the sum of the currents out of that node. So the currents into the node are going to be equal to the currents out. Now a node, as defined, is any point or junction in a circuit where two or more components are connected. Now let me give you the formula for IT. IT is equal to I1 plus I2 plus I3. Now let's look on the diagram and see how that works out. Okay, notice here that we have I1. We have the current coming into the node out of the negative side of the battery into the node. This is the node right here, node A. And the current divides into three different currents. I1, the current is going to go this way through this branch. It's going to go this way through this branch over to the plus side. The current through this node is going to go through the node and out the other node and add to the total current. And the same with I3. Now, Kirchhoff's current law, the current into a node equals the current out. Let's look at that. Let's say, for example, we have 10 milliamps coming out of the negative side of the battery, and I'll write that down so you won't forget it. 10 milliamps coming out of the negative side of the battery going into this node A. That current's going to divide. It's going to divide up. Part of it's going to go this way, part of it's going to go this way, and part of it's going to go this way. But we know that the current into one node of the parallel circuit is going to equal the current out the other node. Now, this may not seem significant right now, but it's going to help you to solve many problems. Okay, I'm going to stop at this point. I don't want to make this too long and too tedious, but you really should, and I think we've actually stopped. I don't want to make this too tedious, and I've lost my video again. I don't know why. There it comes. Okay. So what I'm going to do is suggest that you go ahead and get your textbook between now and Tuesday, and I would like to see you have at least read the complete chapter. You've had quite some time now, and you'll be able to better understand what I'm talking about when you in fact have read this. And you and I have covered some of this in class. In fact, we've covered all this in class. This is a review. Okay, I'm going to close the video now, and I'm not sure if I'll get another one out today, but if I don't, that doesn't mean that you can't go ahead and work yourself. Thank you.